Okay, so yeah, let's go ahead and get things started here. So does anyone have any questions from the exam review, or also old homeworks and other sources are fine as well? Does anyone have any questions that you'd like to go over?
I just had a quick question, just about if there's any like old finals, like we had like old exam 1, 2, and 3, like PDFs. Are there any kind of like old final
Oh
PDF?
yeah, I meant to post that earlier. I could put some up after this meeting if you want to look at those.
That's perfect. Yeah, because I feel like I'm starting to just like remember what the answers are for the practice one, and it's
Mhm.
like,
Yeah, I'll put that up after this meeting.
thank you.
No problem. Yeah, anyone have any questions you'd like to work out or do?
Would you mind doing number 2 on the practice exam?
Yeah, absolutely. Let's see. All right, number 2. Okay, so use the squeeze theorem to evaluate the limit. So this is the limit as x goes to 0 of x arctan of 1 over x. All right, so let's see here. So if we send x to 0, we have this going to 0, but then this isn't going, it's not really clear what's happening with this because we have something getting really tiny in here, and then we have 1 over that. So whenever we have 1 over something, or like something going to infinity in here inside a function that's bounded, that's a good time to use the squeeze theorem. So arctan of 1 over x, and really arctangent of anything, will always be less than or equal to pi over 2. Pi over 2 is the largest possible value that arctan can take, no matter what its input is. And along the same lines, arctan of 1 over x also needs to be greater than negative pi over 2, because that's the lowest possible value that arctangent can take on. All right, so now I have this inequality right here. Now I'm going to multiply everything by x, because we need that as well. So we know the negative pi over 2x is less than or equal to arctan of 1 over x is less than or equal to pi over 2 here. All right, so we have that. And then now what we're going to do is we are going to take the limit as x goes to 0 for all of this. So this is essentially what the squeeze theorem allows us to do. Is it allows us to extend limits through these inequalities here. Oops, there should be an x here. Pi over 2x. All right, so if we look at the left limit here, we're going to have the limit as x goes to 0 of negative pi over 2x. That's going to head to 0. And then we have our limit here in the middle. And then over here, the limit as x goes to 0 for this will also be 0. Okay, so whatever this limit is, it needs to be greater than or equal to 0 and less than or equal to 0. But of course, the only way you could be less than or equal to and greater than or equal to the same number is if you are that number. That means that by the squeeze theorem, it's sort of squeezed in between these two right here, our limit has to be 0. So that's how we use the squeeze theorem. We write down how our part of our function is bounded. We modify it to get it to look like what we have in the limit. We do the limit of everything, and then it's going to be sandwiched in between two different numbers. All right, that was good practice here. Yeah, anyone have any other questions?
Could you do number 11 on the practice?
Yeah, number 11, absolutely. Let's do that one. Just a second here. Number 11. All right. A driver goes 20 miles in 15 minutes on a highway. What is the highest speed limit in miles per hour for the highway that guarantees they were driving over the speed limit at some point in their trip? Now I realized after I kind of wrote this question that that's, I don't know, a little bit misleading what I want. Here's kind of what I was going for with this. So what we're supposed to do here is we're supposed to use the mean value theorem. And our function for this will be s of t, which is our position. So we know that our position at time 0 is 0. And then after 1/4 of an hour, we end up with a position of 20. So this means that by the mean value theorem, there's got to be a place within that 15 minutes where the rate of change of our position is s of 0.25 minus s of 0 over 0.25 minus 0. All right, if we actually compute what this is, this will be 20 minus 0 is 20 divided by 0.25. So this will be 80. And s prime, the derivative of the position, is a velocity. So what this is saying, what the mean value theorem is telling us here, is that somewhere along the line, this car must have been going 80 miles an hour. It could be have been going faster than 80 miles an hour, could have been going slower than 80 miles an hour for other parts of this interval, but somewhere in that 15 minutes, it must have been going 80 miles an hour. So to answer this question, if the speed limit was, say, 75, then we know that person would be speeding. If the speed limit were 79, we know that person would be speeding. So where that kind of ends, where we can't really know for sure if they're speeding anymore, is when this ends up equaling 80. Because at 81, we definitely don't know if they're speeding or not. So I was kind of asking for the threshold on which we knew they were speeding. So the answer is going to be 80 here. And on the final exam, I changed this question to be a bit more clear what I want. But the main point is to use the mean value theorem for this.
Okay, thanks, Professor.
No problem. Yeah, does anyone have any other questions? Anything else you'd like to go over? To be clear, when I say the final exam will be similar to the practice final, is that the final exam review? Yeah, that's what I meant. Yeah, it's the final exam review.
So it's similar in like the way it's been similar for other exams, like for the exam 3, how it was very similar to the practice exam. This
Yeah, it'll
final.
be kind of like 2 and 3. Yeah, exactly.
Okay.
Yeah, anyone have any other things you'd like to work out?
If no one
can I
else
go
has
up?
anything, oh wait, go ahead. Yeah.
I was gonna say to go over question 7 on the review.
All right, number 7. Let's see, what's that one? All right, this is another limit question. Evaluate the limit as x goes to 0 from the right of sine of x raised to the sine of x power. All right. So if we try to plug in 0 right away for this, sine of 0 is 0, and sine of 0 is 0. So we end up getting 0 to the 0, which is one of the 7 indeterminate forms. That means it's not immediately clear what this limit is going to be. Now, the good news is that if it were one of the indeterminate forms, then we could use L'Hopital's rule. And this is what's called an exponential indeterminate form. When we have 0 to the 0, infinity to the 0, or 1 to the infinity, we have something raised to something else, and we get a problem. So the way we deal with any of these situations is we change this to be e to the natural log of whatever our original expression is. I'm going to rewrite this as e to the ln of sine of x to the sine of x power. Now, the whole reason why we do this is because we can exploit the log rule and have whatever is in the exponent here come out to the front. And another thing I'm going to do is I'm going to move the limit inside my exponent, which I am allowed to do that. So I'm going to move the sign out front, sine of x ln of sine of x, like that. And then now if I plug in x equals 0, I have sine of 0, which is 0. And then I have this heading to 0, but as the inside of a log heads to 0, that goes to infinity, or negative infinity. So this is 0 times negative infinity. All right, now in order to fix that, I'm going to move sine to the denominator here. So we have ln of sine of x. And then if I move this to the denominator, it becomes 1 over sine of x. But another way of writing that is cosecant of x. All right, so we could rewrite our expression this way. Now, if we send x to 0 from the right, we have negative infinity on top, and cosecant is 1 over sine, so that's going to go to infinity on the bottom. So we have an infinity over infinity limit, and this is where we can use L'Hopital's rule. Because we can only do that when we have infinity over infinity or 0 over 0. Okay, so upon using L'Hopital's rule, what do we get? Let's see, the derivative of ln of sine of x. So we need to use the chain rule for that. So the derivative of ln of something is 1 over that something times the derivative of whatever's inside. So that'll be cosine of x. All right, now we do the derivative of the bottom. The derivative of cosecant is negative cosecant cotangent of x. All right, now at first, like it looks like this isn't really any better than before, but there's actually something that we can cancel out here. What can we cancel out in this expression? What is the top the same thing as?
When you cancel the cosecant and the 1 over sine.
Oh, you could do that. I didn't notice that. I was more thinking that we have cosine over sine here, which is the same thing as cotangent. So this cosine over sine is cotangent. So that will cancel with this cotangent. But you would have gotten to the same place if you would have done cosecant as well. All right, so since we've done that, we have 1 over cosecant. That's the same as sine. Negative sine of x right here. And then finally, when I send x to 0 for sine, sine of 0 is 0. So I have e to the negative 0. So that will just be 1. So my limit here ends up being 1. Now, one really common mistake with these types of limits is to forget about the e in the bottom here. So I know it's kind of annoying writing it every time, but don't forget to write your e here because 0 wouldn't have been the correct answer. It's going to be 1. All right, so that's an exponential form for L'Hopital's. All right, what else you guys got for me? Number 14, how do you know to take the antiderivative instead of just plugging t equals 2 and t equals 1 and subtracting? All right, well, let's review what number 14 is. So 14, scroll down to that. A company produces unicycles at a rate of f of t equals 3t squared minus 4t plus 45, where t is the number of weeks the company has been in operation. So the question asks, how many unicycles did the company make during the second week of operation? And one thing to note is that it doesn't say during the first 2 weeks, it says during the second week specifically. So we're going to go from the end of week 1 to the end of week 2 here. Now, how do we know to do the integral or antiderivative of this rather than just doing f of 2 minus f of 1? It's because of this word right here, it's rate. So if you ever integrate something from a to b, that's a rate, then you end up getting the net change in whatever it is. So in our case, if we integrate the rate at which we're producing the unicycles from 1 to 2, we can see how our number of unicycles changed over that time. And that will give us what we want to know. So we're going to do the integral from 1 to 2 of our rate, which is 3t squared minus 4t plus 45. And we're doing this for 1 to 2 because we want to start at the end of the first week and then go to the end of the second. All right, and then now we just go ahead and do this. We integrate 3t squared to give us t cubed. we raise the power to 3, and then we divide by 3. We find the antiderivative of this, which will be negative 2t squared. And then we do the antiderivative of 45, which is 45t. We have this going from 1 to 2 here. All right, so now when we go ahead and plug this in, let's see, 2 cubed is 8, minus 2 times 2 squared, which is also 8, plus 45 times 2 is 90. That's what we have here. And then we subtract and we plug in 1 for the cube. We subtract 2 times 1 here, and then we add 45. All right, so these numbers cancel out. This ends up just being a negative 1. So this is 90 minus 44, which is going to be 46 here. So the amount that our number of unicycles changed during that second week was 46. So that means we need to have made 46 of them during that second week. Does that make sense? Was that okay? All right, yeah, so it's integrating a rate that will give you the net change. All right, we're doing pretty well so far. Anyone have any other questions?
Professor, can we use the squeeze theorem with tangent and cotangent?
No, we can't do it with those, because if we look at the graph of tangent, unlike sine and cosine, which are bounded between negative 1 and 1, tangent can go as far down as we want. So there's no limit to how low tangent can go and no upper limit to how high it can go. We can only really use the squeeze theorem on things that are bounded between two finite numbers, like sine or cosine.
Okay, thank you.
All right, we have a question from the chat. Can we go over question 19, please? Absolutely. 18, 19. All right, a particle moves in a straight line so that its velocity at time t is given by v equals t squared minus 3t inches per second. Find the displacement of the particle after 4 seconds. All right, so let's see here. So this is actually going to be another instance of net change. So if we think about it, the velocity is the rate of change of the position of the particle. So if we integrate for 0 to 4, then we're going to get the total amount of displacement. We have 0 to 4, and our velocity was t squared minus 3t. All right, so we do the antiderivative, and then we end up with t cubed over 3 minus 3t squared over 2 from 0 to 4. All right, and then we go ahead and plug in our 4 into here. So we end up with 64, which is 4 cubed over 3, minus 48 over 2. All right, then we subtract when we plug 0 into this, but that will just be 0 here. All right, so if we rewrite this, so this will be 64 over 3, and 48 over 2 is 24. Now I want to combine this into one fraction. So I have 64 over 3 minus 72 over 3. That's how we write 24 in thirds. And we end up with negative 8/3. So that's actually going to be our answer here. So what happens with this is we end up moving forward. We end up moving backward a little bit, and then we move forwards, but not enough to overcome how much we move back. So overall, we are negative 8/3 back from where we started. You can get negative values for displacement. All right, so that's number 19. Can we go over number 12? All right, so I think this one is talking about how we can make a function be continuous and differentiable. All right. So for this one, our goal is to find a and b, so these are constants, such that the function, which is ax squared plus bx plus 1 for x less than or equal to 1, and it's 2x plus b for x greater than 1, is continuous and differentiable everywhere. We want to be able to draw this without picking up our pen, and we want to be able to evaluate the derivative anywhere we want. Now, this is just a polynomial on either branch of this, so it's going to be continuous and differentiable no matter what we pick for a and b away from 1. But when these two functions meet at 1, there's a possibility they could meet like this, where they wouldn't be continuous, or they could maybe meet at the same point, but then have like a sharp corner or something that would cause them to not be differentiable. So it's really at this threshold of x equals 1 where stuff can go awry. So in order for two functions to be continuous, or for a function to be continuous, we have to have these two ends meet. So what I'm going to do is I'm going to plug in x equals 1 for both of these, and they need to be the same. So if I plug in x equals 1 here, I have a plus b plus 1. And that's got to equal what it is on the other side, which is 2 plus b. All right, so we get this from the function needing to be continuous and for these two to meet at this threshold of 1. All right, well, what we can do here is we can cancel out the b's. We can subtract 1 over here. And we see that in order for this to work out, in order for it to be continuous, we need a to equal 1. A equals 1 is going to guarantee that we're going to be continuous here. Now, for differentiable, what needs to happen there is that the derivatives of these two need to end up meeting. Because if they have different derivative, that would be like the tangent line pointing two different ways, and that's going to make a kind of a sharp angle. So we need the derivatives of these two to match as well. So I do the derivative of my top here, and I have 2ax plus b. And then on my bottom, I do the derivative, and I just get 2. All right, now I already know what a is. A is 1. And I know that I'm doing this at x equals 1. So I plug 1 in for both of these, and I get that 2 plus b needs to equal 2. But the only way you could add something to 2 to get 2 is that if the thing you add is 0. We end up getting that b needs to be 0 in order for this to be differentiable. So a equals 1 made it continuous, and b equals 0 made it differentiable. But the way we did it is we set both the regular equations equal to each other at that x value, and we set the derivatives equal to each other at that x. All right, that was a good one. Anyone have any others or any other topics you'd like to discuss?
I'm a little bit confused with question 16. I keep getting 25 for the answer, so if you could do that one.
Okay, yeah, we'll do that one once we do number 20 from exam 2.
Okay.
All right, so 20 from exam 2. Let me pull up exam 2 real quick. Let's see what that is. Assignments. And 2. Okay. All right, just a second here, it's loading. Oh, according to my thing here, it only looks like I have 18 questions for exam 2. Can you describe what the question is? Number 18? Oh, okay. All right. So this one wants us to find the slope of the tangent line, aka the derivative. So find the slope of the tangent line to h of x equals x to the x squared at x equals 2. All right, so what we're going to do here is, in order to do this, we need to use logarithmic differentiation, because we have this kind of crazy exponential tower going on. So we see that ln of h of x must equal ln of x to the x squared. And what this will allow us to do is this will allow us to move the x squared out to the front. This will be x squared ln of x here. Just a second here. All right, so now that we have this, we're going to do the derivative of both sides here. So I do the derivative of ln of h of x, so that'll be 1 over h of x. And then I multiply by the derivative of the inside, which will be h prime, and that's what I'm trying to get. Then I'm going to do the derivative of this part right here, and that will require me to use the product rule. So I do the derivative of x squared, which will be 2x, leave the natural log alone. And then I leave the x squared alone and do the derivative of ln of x, which is 1 over x. All right, so we got this. And then finally, I'm going to move h of x back up here. And that gives us that h prime of x will be x to the x squared times 2x ln of x. And then this will simplify to be an x. All right, so that's what h prime is. And we want to know what h prime of 2 is, because we want to find the slope of the tangent line at 2. Okay, so this will be 2 to the 2 squared, which is actually 2 to the 4th. And then we have 2 times ln of 2 plus 2. So lots of 2's everywhere. And we could factor out a 2 from all of this. So we have 2 to the 5th, 2 ln of 2 plus 1. So this will be 32 times 2 ln of 2 plus 1. Right here, after we do all the 2's with this. All right, so the key to this problem, though, was the beginning here, where we use logarithmic differentiation to make it something that we could actually do the derivative of. All right, so there we go. Got that one. All right, yeah, what are the, oh yeah, that's right, we're gonna go to number 16 from the practice final next. Okay, find the largest volume of a box with an open top, square base, and surface area of 75. Okay, so we're looking for the maximum volume. We have an open top, we have a square base, and we know that the surface area must be 75. Okay, so let's see here. Well, let's draw our box. So we know that our box has a square base. So I'm going to call the side lengths of that base x. And then it's going to have some height here, which I guess I'll just call this height y. So we know that v is the length times the width times the height. So it'll be x squared y. So this is the function that we want to maximize here. Now, the problem with this is that we have more than one variable, and we're not in Calc 3 yet, so we're not going to do multivariable calculus on this. We need to get things to be a single variable. Now, how do we do that? Well, we use the fact that it's a square base, but we haven't done anything with the surface area yet. So the surface area needs to equal 75, but we can also get the surface area in terms of the variables here. So the surface area includes this square at the bottom. It includes an x squared. And then it also includes the 4 sides of this box. So we have the area of each one of the sides is x times y, and then there are 4 of them. So we have 4xy for that. And then since it's an open top, we don't have anything up here. If it didn't say open top, then this would be 2x squared, because we would also have the top of the box. All right, now we're going to solve for y so we can substitute it into here. So we have 75 minus x squared divided by 4x when we do the algebra, and that's going to give us y. Okay, so I'm going to take y, I'm going to substitute it into here so we only have one variable. So I have x squared, and I have 75 minus x squared over 4x. All right, before I do the derivative here, I'm going to simplify this. So I'm going to move a 1/4 out, and I'm going to multiply, well, I'm going to cancel these x's, and I'm going to multiply the x through here. So we have 75 over 4x, and then we have minus x cubed over 4 right here. All right, so we have that. So now what we're going to do, that we have our volume, is we're going to take the derivative of it, and we're going to set it equal to 0. So we have dv dx. So we have 75 over 4 minus 3x squared over 4. All right, now the critical values, i.e. where a min and max could occur, would be where this is equal to 0. So I'm going to multiply both sides by 4, get rid of those. I'm going to add the 3x squared over here and then divide by 3. So we end up getting that 25 is x squared. Well, that can only mean one thing. It means that x is equal to 5. And we ignore negative 5 because that can't be 11. So we see that x equals 5, but that's not the right answer here. They asked us for the volume of the largest box. So what we need to do is we need to take our 5 and we plug it in to our volume formula here. So we're going to do that. All right, so our volume will be 75 times 5 minus 125. All of that will be divided by 4. All right, 75 times 5, I believe, is 375. 375 minus 125 is 250. And then 250 over 4 can be simplified into 125 over 2. So that's going to be our volume here. And by the way, some of you who may have done the practice exam earlier may not have seen this answer on there. That's because I accidentally messed up when I was typing in the answers. But if you take it now, I changed one of them to be this 125 over 2. So if you got that answer, you didn't do anything wrong. I just accidentally put in the wrong number. All right, let's see here. We got a question in the chat here. Let's see what this is. All right. So this question asks, determine the value of A such that f of x is continuous at x equals 2. Okay, and then they give us this piecewise function here. So f of x will equal x over a for x less than or equal to 2, and then 1 over x plus 1 minus 1/3 over x minus 2 for x greater than 2. All right, so let's see here. Now, this might look a little bit familiar here, the way that this is written out. Does anyone know what this is right here? What kind of thing would we be computing if we wrote out something like this? A little bit hard to spot.
Is it a limit?
Yeah, so what we're going to end up doing is we're going to do the limit as x approaches 2 for this. Because we can't just plug in 2 like a lot of the other ones, because then we'd be dividing by 0 and that wouldn't work out. So what we're going to do is we're going to look at the limit as x approaches 2 of this. And whatever that is, that's what this needs to be coming from the other side. So whatever we get for this, this needs to equal 2 over a, because it needs to agree with the side over here. So whatever this limit ends up being, it needs to be 2 over a, or we need to pick our a such that those are the same. All right, so let's see here. There's a quick way to do this one that's a little bit hard to spot, or we could just do common denominators here. And I'm going to do that just in case we don't see the slip rule. So I'm going to multiply the top and bottom of this by 3. I'm going to multiply the top and bottom of this by x plus 1. And then we still have our same denominator. Okay. So we have 3 minus x plus 1. That will simplify to be 2 minus x. And then now our denominator will have 3. It'll have x plus 1. And it'll have this x minus 2 right here. Because what I did was I combined these fractions together, and then I have a fraction divided by something. That means that this will also go in the denominator here. Okay, now there's a little bit of simplification we can do with this. What can end up canceling here? What things look kind of similar? The x minus 2 and the 2 minus x, absolutely. So x minus 2 is actually the same thing as negative x minus 2. So this and that will cancel, and we end up with a negative sign from it. And so we have 1 over 3 times x plus 1. And now that's good news because there's no more x minus 2 to worry about down there. So what I can do is I can send x to 2. So this will be 3 times 3 is 9. So I end up with negative 1 over 9. Now remember, my whole objective here was that whatever I got from this needs to equal 2 over a. So I'm going to multiply both sides by negative 9. So 1 is negative 18 over a, or a needs to be negative 18 for this to work. All right, so there we go. So that's the long way of doing this. There's actually a quicker way of doing this. So you may remember, or you may have forgotten, one way of defining the derivative of a function at a point is the limit as x goes to that point of f of x minus f of a over x minus a. And that's actually what's happening right here. We're doing the limit as x approaches 2, we have the x minus 2 down here, and it seems like the function we have up here is 1 over x plus 1. So rather than doing that limit, we instead look for f prime of 2 if f of x is 1 over x plus 1. So another way of writing this is 1 plus x to the negative 1. So f prime will be negative 1 over 1 plus x squared, and then we just plug in 2. So we end up getting 2 plus 1 squared is 3, and then we have our negative. So we end up getting that that's negative 1/9. And then we don't have to do limits at all. We just had to realize we're approaching 2 as we get here, and that this is a derivative. So we could have done it this way too, if you really don't want to do all this algebra with the limits. But either way, we end up getting that a is negative 18. Did that make sense? Was that okay how we did this problem? All right. Yeah, we just needed to make sure that both ends of this ended up agreeing. All right. Yeah, we got time for a few more for sure. Anyone have any other ones you'd like to go over?
Can we do question 18 from the practice exam, please?
Yeah, absolutely.
Thank you.
Okay, number 18. Find the area of the largest rectangle that can be inscribed in a right triangle with legs of length 3 and 4. If 2 sides of the rectangle lie along the legs. All right, so they give us this picture here. It looks something like this. So this length is 3. This length is 4. And then we have our rectangle here. And I drew it to look like a square, but it doesn't have to be a square. In fact, I don't think it can be a square. And then this length is going to be x, and this length is going to be y. And our goal is to try to find the largest rectangle we can have, or the area of the largest rectangle. All right, so the area of this rectangle is x times y. As with all the other optimization problems we've done, we can't do them with two variables. We need to only do it with a single variable. So you need to be able to eliminate one of these somehow. Now, one piece of information we know is that a corner of this square is on this line right here. So if we can find an equation for this line, then we have a relationship between x and y that we can use. All right, so let's try to figure out what the equation of this line is. So lines have the form y equals mx plus b. Let's see, b is going to be the y-intercept of this line, and actually we know what that is. The y-intercept is 4. That's how high this is. So we know our line's got to be something like mx plus 4. Then we could proceed in two different ways. We could plug in the point 3, 0, and then see what m has to be. Or we could observe that if we move over 3, so we have a run of 3, we end up going down by -4. So this means that our slope has to be -4/3. All right, so there we go. So however we do it, this is going to be the equation of our line here. And now, conveniently, this line equation gives us a relationship between x and y. So we could substitute this in for the y, and then we only have an equation with x's. We have x times 4 minus 4/3 x. And if we were to FOIL that, we have x minus 4/3 x squared. All right, so this is our area function. So let's do the derivative of it and see where it's equal to 0 to find the critical points. So we do the derivative of 4x, it gives us 4. And then we do the derivative of -4/3 x squared. So we bring the 2 down, making it 8/3. And then we have x right there. All right, so we want to see where this equals 0. So we add the 8/3 x. And let's see, we can multiply by 3, divide by 8. So we have 12/8, which is also 3/2. And that's going to be our x here. Now remember, 3/2 isn't what they wanted here. They didn't ask for the dimensions of this rectangle. They asked for the actual area here. So we need to take this x and plug it into there. So you need to be very careful about what they're actually asking these questions. Sometimes they will ask you the dimensions, like what is the x length of this box, what is the y length? But this time they want to know the area. So my area is 4 times whatever x is, so 4 times 3/2. And then we subtract 4/3 times 3/2 squared. Okay, well, let's see. 4 times 3/2 is 6. If I were to square this, I would have 9/4. Okay, that's pretty nice because these cancel out. And then 9/3 is 3. So we have 6 minus 3 is 3. That's going to be the area of the largest rectangle that we can have here. All right, anyone have any questions on that? Was that one okay? All right. I think we have time for a few more, maybe. Oh yeah, we have 15 minutes, definitely. Anyone have any other ones? We do number 8 from the exam review. All right, let's check that out. Okay, this one's about finding the absolute minimum value of a function. All right. So this time, the function in question we want to minimize is x squared e to the -x. And we're doing this on the interval 1 to 3. So we want to find the smallest value that this function takes on that interval. Okay, well, the way we do that is we first find any critical points that are in that interval, and then we compare the value of the critical points with the value of the endpoints, and we see which one of those is smaller. So to get a critical point, we find the derivative. The derivative of this requires us to use the product rule. So we do the derivative of x squared, which is 2x. We leave this one alone. And then I leave my x squared alone, do the derivative of e to the negative x, which is negative e to the negative x. All right, now I want to see where this is equal to 0. All right, now there are two ways that we can get a critical point. We can get them when our derivative is 0, when it's undefined. Now, exponentials and polynomials aren't undefined anywhere, so that's not going to happen. So we're just going to see where this is 0. So if I factor out an e to the negative x, I have this right here. And e to the negative x can never be 0. E to the anything is never 0. So we're really just seeing where 2x minus x squared is 0, or 2x equals x squared. And there are two x values where that happens. The x equals 0 and x equals 2. Now, if our interval were bigger and it included 0, we would definitely consider 0 as a possible minimum value. But the thing is that we're only looking at the x values on the interval 1 to 3. So we're going to ignore 0 for this, but we will include 2 because 2 is in fact between 1 and 3. All right. We have x and we have f of x. Now let's see which one of these is the smallest. Between 1, an endpoint, 2, which is a critical point, and 3, which is the other endpoint. So if I take 1, I plug it in here. I have 1 squared is 1 times e to the negative 1. That's 1 over e. Okay. I take 2, I'm going to plug that into here. That's going to give me 4 over e squared. Then I'll take 3 and plug that into here. That's going to give me 9 over e cubed. Now, at first, it might seem like it's kind of hard to know which one of these is the smallest, because our denominator is getting bigger, but our numerator is getting bigger too. So let's try to find a way to compare these. I'm going to try to compare these to the size of 1 over e. So the way I can get a 1 over e here is if I rewrite 4 over e squared like 4 over e times 1 over e. Now, 4 over e is bigger than 1, right? Because e is 2.7 something, 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 and 4 is, well, 4. So this number is bigger than 1, and we're multiplying it by 1 over e. That means that this number, whatever it is bigger than 1 over e. So we're definitely not including 2 here. 2 can't be a minimum because we know 1 is smaller. Now let's see if we could do something similar for the next part. We have 9 over e cubed. We could rewrite that as 9 over e squared times 1 over e. Now, using the same reasoning, we know that 9 is bigger than e squared. And how do we know that? Well, 3 squared is 9, but e is even less than 3. So if we square that, we're going to get something that's less than 9. So this number is also bigger than 1, meaning that this is also bigger than 1 over e. So it seems like this is going to be the smallest one of the bunch, and we want the value, the function value. So our answer for this one is going to be 1 over e. So when in doubt with these kind of weird numbers, sometimes you could do things like this to compare the size of them, even if you don't know what these numbers are. All right, let's see. I think we had a few other questions while I was doing this one. Can we do number 4? Yeah, let's check out number 4. Have we done number 11 yet? Yeah, we did 11 earlier, but don't worry, I'm going to post this to YouTube so you can go back and look at it. Okay, use a left Riemann sum with 4 rectangles to approximate the integral from 0 to pi of cosine of x dx. Now, since we've learned the fundamental theorem of calculus, we know how to compute this exactly, actually. We find the antiderivative of cosine and then plug in pi and 0. But this is asking us to approximate something. So don't be tricked. Don't actually solve the integral. Use Riemann sums to approximate. All right, so we have 0 to pi of cosine of x dx. Okay, and we want to use n equals 4 rectangles, and we're going to use left endpoints with these rectangles. Okay, so how are we going to do this? Well, let's see here. So the interval that we're finding the area under the curve is 0 to pi. So we're going to divide that up into 4 pieces. This means that pi over 4 will be the width of all of our rectangles here. The width for each of them will be pi over 4. All right, now how do we get the height of each of them? Well, what we do is we use the left-hand endpoints of each of these intervals. So our Riemann sum, our left Riemann sum, will be cosine of 0 times pi over 4 plus cosine of pi over 4 times pi over 4 plus cosine of pi over 2 times pi over 4 plus cosine of 3 pi over 4 times pi over 4. And with left-hand endpoints, we stop one increment short of whatever this is. Now, if I asked you to do right-hand endpoints instead, for example, we wouldn't include the 0 in the front, but we would include a cosine of pi times pi over 4 at the end here. So the left and right-hand endpoints only differ by 1 term. All right, now we know what each of these is on the unit circle, so let's go ahead and compute that. Cosine of 0 is 1, so pi over 4. Cosine of pi over 4 is root 2 over 2. Cosine of pi over 2 is 0. And cosine of 3 pi over 4 is negative root 2 over 2. Okay, well, this is actually pretty convenient because this and that will cancel out. So that just leaves pi over 4. So it turns out that pi over 4 will be our left-hand Riemann sum for this integral right here. All right, so we got that one. Sydney would like to do number 20 from the review. And if we have time, maybe we'll take a look at 2 or 3. By the way, you guys can email me. I'll do my best to get back with you if we don't make it to one of your questions. All right, let's go to number 20 here. All right, what does this one say? If the radius r and height of a circular cylinder both change at a rate of 2 centimeters per second, how fast is the volume of the cylinder changing at the instant where r is 10 and h is 20? Okay, so we have a lot of information here. So we know that r is 10, h is 20, and we know it says the radius and height change at a rate of 2 centimeters per second. I guess it doesn't say increase or decrease, so I'm just going to assume it's positive since all the answers here are positive. So we're going to have the r dt equals 2 equals the h dt. And our goal for this problem is to figure out what dv dt is going to be. Okay, well, if we want to know something about the volume here, what's going to happen with this? So the volume, we know that's equal to pi r squared h. Okay, but I'm interested in the derivative of my volume. So I need to do the derivative of this. Well, let's see. That means the dv dt. Okay, now pi is a constant. I don't need to worry about that. But I am going to have to use the product rule for this. So I do the derivative of r squared, giving me 2 pi r dr dt. And then I left the h alone, so I don't have any dh dt right now. Next, I take the derivative of the h and leave the r squared alone. So I have pi r squared the h dt. All right, so there we go. There's our derivatives, and we needed to use the product rule and implicit differentiation to do this. Okay, now we actually have all of the information we need to plug in for all of this to get what we want to know. This will be 2 pi times r, which is 10, times dr dt, which is 2, times h, which is 20. Then we have pi, we have r squared, which will be 100, times dh dt, which is 2. Okay, so let's see. 2 times 2 times 2 is 8. And then we have 2 zeros here. So it'll be 800 pi. This will be 200 pi. So combined, that will give us 1,000 pi. That's going to be dv dt. So what you can see here is that even though our rates of change for the radius and height are actually very small, because the volume is a product of those, we're multiplying all that together, we end up getting something rather big for the rate of change of our volume here. All right, so that's how we do that one. Let's see here. Oh, for those who took the makeup exam 3, will we also get additional points from the curve? Yeah, you will. Yeah, it's only fair because it was essentially the same exam. So yeah, that'll happen. All right. Let's see. We maybe have time for one more here. Oh, we already did number 2. So how about for Donald here, we can do number 3. Let's take a look at that one and then we'll call it a day here. So this one has us do the integral from 0 to 1 of x e to the x squared. Okay, now we haven't learned any kind of product rule or anything like that for integrals. So what are we supposed to do with this? Well, we really only know one technique of integration at this point, and that's u substitution. So if we're stuck on an integral, u substitution is all we really have to work with. Okay, now my 2 pieces of advice for picking a u substitution are make sure it's in your integral. That one's kind of a no-brainer. But the one that's easier to forget is make sure the derivative of your u is also in your integral. So for this one, I think I'm going to pick u equals x squared, because obviously x squared shows up here. But if we do the derivative here, then we see we have an x dx in both the du and in the actual integral. The only problem is we don't have this 2 here, but that's an easy fix. We could divide by a 2. There, now we know that 1/2 du must be x dx. Okay, so now we can convert this over here. Oh, why can't we use the product rule for integrals? That's a question I would maybe save for Calc 2. We actually talk about that stuff in Calculus 2. But kind of the short answer is kind of like how multiplication and division didn't work well for derivatives. It's also not going to be that nice for integrals either. Okay, so we're going to take this and put it into here. So we have 1/2 the integral. Now this x dx, I sort of exchanged that for this 1/2 du. So we don't have the x dx anymore. You have a du. And then this is e to the u. Okay, now one part that confuses a lot of people is what to do with the bounds when we have a definite integral here. So the way we make new bounds for our integral here is we take our old bound and we plug it into our formula for u. So I take x equals 0, which is my old lower bound. I plug it into this formula, and I have 0 squared, but that's also 0. So I'm going to keep the same lower bound. Then I take 1, I plug it into here, and I have 1 squared, which that's also going to be 1. So in a pretty huge coincidence, we actually don't change our bounds for this one. But if you ever do need to change the bounds for doing a u substitution, that's how you do it. You take the old x value for your old integral, put it into your formula for u, whatever you get out of it is your new lower bound. And then we do the same thing. All right, now we've turned this kind of scary looking integral into a very easy integral. The antiderivative of e to the u is, of course, e to the u. This will go from 0 to 1. And then we plug 1 into here. That gives me e. And then I plug 0 into here, and e to the 0 is 1. So we end up with 1/2 e minus 1, or I think it's e minus 1 over 2 in the answer choices. All right, that's about all the time I have left for today. But yeah, email me with any questions you have, and I'll do my best to respond to you before tomorrow, in case you have any last minute questions here. Other than that, I wish you guys best of luck on the final exam and any other finals that you guys have as well. So I'll see you all later.